Okay, here's our video on heat and heat transfer, phase changes, and temperatures, part 4. And what a perfect day to talk about heat when it's 90 degrees outside or higher. I think it's higher. So you may be saying, well, of course, if it's 90 degrees outside, it must be winter. Well, it could be winter if I'm in Brazil, right? Because it's when it's winter in Brazil, it's summer up here in the United States or Canada. So let's talk about temperature and phase changes. And just to review from the last videos, remember heat does move to cold, and there's a big study on this. And let's get the pen going. It's called thermodynamics. Thermo is that heat. Thermodynamics, I'll talk about in other videos. Right? It's a study of heat. And if you're going to be an engineering student, you'll learn about thermodynamics. And of course, if you're taking more science classes. So before we talk about phase changes and before we talk about temperature, let's look at our nice little ice cubes here. And as you can see, they're melting. So if I had an ice cube, let's get our blue pen going for ice, why not? So if I have my little cube here, right? If I make a two-dimensional diagram of the cube, attempting to anyway, and we'll just say that inside these particles, these atoms, they're kind of, bonded together. Now, even though they're bonded together, we may say, well, in something that's frozen, nothing's moving, but they are. The particles are moving. They're just not moving as much as if they were in liquid state, right? The particles are moving. Everything is moving in the universe. And I've talked about that over and over again. So the particles are moving, and when it moves, remember the energy is kinetic energy, the energy of movement, right? Let's write it again, the energy of movement. So everything moves. The energy of movement. And of course, when we're talking about the energy of movement internally, we're talking also about thermal energy because it is a type of kinetic energy. Right. Okay, so here we have, it's in the solid state. But when we get to a liquid state, do our two-dimensional view of this, see that the atoms, the particles are moving further apart. There's more energy involved. You need more energy to break those bonds. Let's get a better diagram of that. And I'm going to change the pen. So remember the states of matter, right? The states of matter. And there's more than these four. Actually, there's states in between, but we're just going to talk right now. We have our solid state, right? We have our liquid state. We have our gas state. There's also a plasma state. And we'll talk about plasma in other videos, but plasma is just charged gas, ionized gas, like lightning, for example. And again, there's other states of matter, but we'll just concentrate on these states. So, and we were talking about a change of state, right? Not moving from like New York to New Jersey. No, not that. Not that. But a change of state, a change going from solid, let's say, to liquid. That's a change of state. And what is how does this happen? It's because there's a change in a type of energy. What do you think? A change of the average kinetic energy. The average kinetic energy. And the average kinetic energy of a substance is its temperature, right? It's temperature. And again, we can use Celsius, we can use Kelvin, and we can use Fahrenheit. Most of the world uses Celsius. Science uses Kelvin and also Celsius. And only a few countries use Fahrenheit, like the United States, for one. All right, so it's very important. Let me put in a little star here. There's our star. Maybe it's Betelgeuse. Who knows? But it's important to know that when the kinetic energy increases, so I'll write that down. When kinetic energy, or we should say the average, when kinetic energy increases, writing over our ice cubes. And again, the average, when the average kinetic energy increases, we know that the particles inside the substance, the particles are moving faster. So you can think of this basically as higher temperature would equal more what? More kinetic energy. We should say faster. The particles are moving faster. So when the particles are moving faster, you're getting a higher temperature. The faster they move, the hotter it gets. Let's write that down. So let's clear this out. Let's write it again. The faster they move, the faster particles move, the hotter it gets. Right? So, I mean, you can do this experiment by rubbing your hands. So, if you rub your hands, you can feel the heat. Just rub them. Rub your hands. The faster you rub them, the hotter it gets. Of course, you don't have enough energy, unless you're with a Hulk or Thor, to, create fire. But they'll get warm. So, if you think about the temperature outside, let's say it was 90 degrees Fahrenheit, which is very hot, or, basically that's 32 degrees Celsius. And it's about over 300, about 308 degrees Kelvin, maybe less than that. And so if then we had, let's say we had 80 degrees Fahrenheit, which is about 26 degrees Celsius. So which one is the are they moving faster here, or are they moving faster here? Well, they're moving faster. The particles are moving faster at the 90 degrees. They're moving faster. So that should clear that up. Right, and here's a better picture, as you can see, from solid, liquid, and gas. See, in solid, they're together, they're tightly bonded together. It takes a lot of energy to break those bonds, and so it heats up because now the bonds are broken in liquid. You can see it right here in the liquid. There's more space and there's more energy, and so they're moving faster. And in gas, they're moving extremely faster, and it gets hotter. Now here's our teacup and teapot, right? Whatever that tea may be. Maybe it's some kind of jasmine tea. I'm not sure. Well, let's just say it's some kind of tea. So, and let's get our pen going again. We'll use, I'll use, I'll use, who knows? We'll use anything. So let's say this cup of tea is 85. Well, that's not going to work. We'll use green. Green will come out. You were probably saying that to me, right? Let's say the pot of tea was 85 degrees Celsius, and each cup was 85 degrees Celsius. So they have the same temperature, even though the pot has more thermal energy. And we talked about this in the last video. Well, maybe not the last video, but more thermal energy. Right? So thermal energy, the more mass equals more thermal energy. So they both have the same temperature, but the pot took longer to heat up. So if we look at the pot, and so the pot itself, we'll put an arrow going over here, change the pen, get a little blue. The pot took longer to heat up because it has more mass. It's common sense. There's more mass, it takes longer to heat up. It also takes longer to, guess what? To cool down. Very important here. Remember that, right? So the more massive it is, the longer it takes to heat up, and the longer it takes to cool down. So if you were heating up these substances differently in different areas, it would take much longer to heat up the pot of tea, or the kettle, whatever you want to call it, than the cup. Let's look at another example. And we'll use purple. Why not? Make a line over here. We'll separate the page. Let's say that you were putting something in the microwave. You put this thing, maybe it was a Hot Pocket. Who knows what it was? Burrito. And let's say it was zero point 0.2 pounds, whatever that thing is. And let's say you had another one was zero point 0.3 pounds. Well, if you put them in a microwave, and here's our little microwave. Let's say you put them both in the microwave. It's a weird looking microwave, but okay, whatever. And which one would heat up first? Which one will be, let's say you put them both in the microwave, and after 1 minute, which one will be hotter? What do you think? Who wins the prize? Well, this one would be hotter because it takes a shorter amount of time to heat up. Remember, the more massive it is, the longer it takes to heat up. So if you put these two things, Hot Pockets or whatever they are, the heavier one, the 0.3 pounds is heavier, would take longer to heat up. And now we're ready for phase changes. A phase change is when you're going from one state, like this right here in this cube. If you're going from one state, solid, to another state, liquid, or to another state, gas. And there's these couple of vocabulary words here, latent heat and specific heat. So let's just go over those. So when you're going from one change to another, you can see, just look at this graph here. Here the temperature is increasing, but once you get to this part, you can see the temperature is not increasing because this is the beginning of a phase change. And during the beginning of a phase change, temperature does not increase. And you can read it right here. Temperature is constant. And the reason why it is because the heat is needed. Heat is needed to break the bonds. Heat is needed to break the bonds. So all that energy is needed to break the bonds. So the kinetic energy will be the same until those bonds are broken. Very important. You should rewind the tape and listen to that again. So latent heat is the energy required to convert a solid to a liquid or liquid to gas. Latent heat is constant. It's a constant temperature because the heat is needed to break the bonds. So, see if I can clarify that a little more. So, use red. So, inside this solid cube, right, the bonds are tightly packed. We got to break those bonds. And during this phase change, this is what a phase change is. This is the phase change. The latent heat is breaking those bonds. And because the latent heat is trying to break those bonds, the kinetic energy is still the same. That's why the temperature is not increasing. Now, specific heat right here is the energy needed right here to make the change, right? So right here, we'll just put an arrow. Let's clear this up. Just make sure you have this down. Heat is needed to break the bonds in latent heat. The heat is breaking the bonds. Clear this, make it a little easier. So in specific heat, it's the heat that in specific heat, the temperature is increasing. The energy is increasing. The kinetic energy is increasing. It will stop once there's a phase change. So we'll have this as a phase change. And now the specific heat increases again. It's increasing because kinetic energy is increasing. But then we get to a point where we have another phase change. We're trying to break more bonds. And then we have gas. And then we have an increase in temperature again. So think of specific heat as the increase in temperature and latent heat as constant temperature. Remember those two. It's easy to remember. We're going to talk more about phase changes in the next video.